Welcome to day 2 of Chemistry of Gases. We're going to focus on the behavior of gases, gases that might be diatomic molecules, gases that might be polar molecules. We're going to look at a sample of gas like this one and talk about what the kinetic molecular theory says about how these gases behave. Here I have tiny gas particles. The kinetic molecular theory says that gases are single particles in constant motion, and that motion is straight line. When it runs into something else, either a gas particle or the sides of the container, you have a perfectly elastic collision. So imagine any gas sample is a random moving set of tiny particles. Do those particles have charges? Possibly. Do those particles have polarity? Possibly. So that's going to make explaining the behavior of gases a little bit difficult. But remember, without these forces of polarity between atoms and molecules, all elements and compounds would be gases. These forces of polarity, attractions like hydrogen bonding and van der Waals forces, are what makes elements and compounds into solids and liquids. So if we want to talk about gases, we want to talk about situations that minimize these attractions, minimize these repulsions. So we're going to define a term, and that term is an ideal gas. There he is, very ideal gas. The quintessential example of a gas particle. So in the realm of ideal gases, every gas is a tiny particle with no volume themselves compared to the volume of the gas sample. Tiny particles with negligible to no volume themselves, with no attractions, no repulses, no charges, and no phase changes. They won't condense if we cool them down. They won't condense if we pressurize them. These are the terms for an ideal gas. These are the features of an ideal gas. Contrast that with real gases. Well, I have a sample of gas in a container, and that gas will condense at low temperature. If I get it close enough to its boiling temperature, it will condense from a gas into liquid. A real gas will condense at high pressure. If I squeeze it together enough, it's going to condense into the liquid phase. A real gas will have intermolecular attractions, will have positives and negatives, differences in where electrons sit in the molecule, differences in the way electrons are shared. So real gases do have attractions and also repulsions. But here's the thing. All real gases will behave exactly like ideal gases if we keep them at very low concentration, very high temperature, nowhere near their condensing point, very large volumes, where their interactions with one another will be very infrequent and at very low pressures. So we can describe and make predictions about real gases by thinking of them as ideal gases. And there's one great formula that is used to predict the behavior of gases, and that's called the ideal gas law. PV equals nRT. You're going to use this equation a lot in calculations of the chemistry of gases. P is pressure, V is volume, N is the number of moles, T is temperature in Kelvin, and R is a gas constant that does two things. It keeps the proportion equal from this side of the equation and that side of the equation, and it also provides the right units, so the units will cancel out properly, and I'll be able to solve this equation to get temperature, or to solve this equation to get volume, or to solve this equation to get pressure, or even the number of moles. So R is a gas constant. It's called the ideal gas constant, and it'll always be given to you in your reference tables. So let's try to use this ideal gas law in an ideal gas law problem. What volume of fluorine gas at 645 millimeters of mercury and 15 degrees Celsius would 0.833 moles occupy? Okay, well, this is fluorine gas. but we're going to use the ideal gas law, so it doesn't matter what gas it is. All ideal gases look exactly the same. Tiny little points with negligible volume. Let's use the PV equals nRT gas law to solve this problem and figure out volume. So here's what I'm thinking. PV equals nRT, the first thing I need to do is solve this problem for volume. It's asking me what volume, so I rearrange the equation to get V by itself. Not too hard, V equals nRT over P. Second thing I'm thinking, here's the value of the ideal gas constant, 0.0821. And the units are liter, atmospheres per mole per Kelvin. So I'm going to need temperature in Kelvin, and I'm going to need pressure in atmospheres. So the first thing I'm going to have to do is a few conversions. All right, let's do the pressure conversion right over here. 645 millimeters of mercury equals how many atmospheres? 645 millimeters of mercury, and there are 760 millimeters of mercury in 1 atmosphere. Stop. 645 millimeters of mercury divided by 760 is going to be 0.849 atmospheres. And the second thing I need to do is make sure my temperature is in Kelvin. This is not a Kelvin temperature, so 15.0 degrees C plus 273 is going to be 288 Kelvin. So now I have temperature is 288 Kelvin. I have pressure equals 0.849 atmospheres. Volume is going to be in liters, and moles I have. So all I have to do is substitute these values into this equation using this value of the ideal gas constant. Volume will equal 0.833 moles times 0.0821 liter atmospheres per mole per Kelvin times 288 Kelvin over 0.849 atmospheres. Checking the units. Atmospheres will cancel. Moles will cancel. Kelvin will cancel. And I'll end up with a calculation whose units are liters, and liters is what I need for volume. When I solve that equation, 0.833 times 0.0821 times 288, all divided by 0.849, the answer will be 23.2 liters of fluorine. So that's how you solve a gas law problem using the ideal gas law. Now look at the equation, PV equals nRT. You can use this equation to find moles if you need to. You can use this equation to find pressure or even temperature. So I'm going to stop the video now and give you lots of practice using the ideal gas law to solve very different kinds of equations. Thanks for listening.